Okay, so we have many students here. So there are 83 students who enrolled who enrolled this course. Uh, so, so I believe the computer engineering department, the the registration is very difficult, right? Because there are many students here, and then many students want to take the computer engineering or computer science course. So I think this is a kind of some precious chance for studying computer engineering course here. So sorry for the some lack of resources, but you succeed to register this course, so study hard for one semester, right? Okay, what did we learn in the previous class? So did you remember? Do you remember? What did we learn? So we learned how to design. So we learned about some concepts for digital design, right? Some approaches and then some principles for designing digital systems, right? So I mentioned that. So currently, the digital systems are very complex systems, right? And previously, so we can just integrate thousands of transistors, but now, so this is the old generation chip, actually, old generation hardware architecture. The hardware architecture of Intel CPU, but you can find that it is old architecture, so not the cutting edge architecture, but even this old architecture includes billions of transistors. So, the digital systems are very complex systems. Then I also mentioned that, then how can we design these complex systems? So this is some concept or these approaches for designing complex systems. So abstraction, discipline, and then hierarchical design and modular design, and then regular design. Okay. So what is abstraction? Abstraction means that so we can hide details when these details aren't important. Okay. So if I mentioned that, so also computer systems are very complex systems. So and then it is very tricky to understand the entire aspect of computer systems, right? So we just focus on a certain layer of a computer system, and then which means that we just focus on details of a certain layer, but we just ignore some content or some details of other layers. This is a concept of abstraction, and then this abstraction concept is widely and then frequently used for understanding complex systems. So, for example, we just understand how to drive. Okay, we just know how to use handle or accelerator pedal, but we don't know the details of car system, right? And then discipline, so intentionally restrict design choices. It is because the real world system is very complex, but we just restrict some design choices. So example is the digital design, right? Even though the real signal or real data is very complex, and then also it's an analog signal, but we just understand this analog signal like the 1010, so restricted. Okay, the signal level or some data representation is restricted. And then hierarchical design, modular design, and then regular design. So hierarchically, so we can understand some complex systems hierarchically, right? we can start from the some large system here, and then this large system is separated to the smaller modules. Okay, here. Then this is the hierarchical design. Also, modular design means that so we can just understand a certain module like the functions, a function of a certain module and interface. So the interface is the some port. So and then through these ports, like through this input and output port, signals are connected to other modules. Okay, so this is the modular design, and then regularity. You can understand that regularity is the copy and paste, right? You can just copy the same module to the another space. So this is how we can design the complex the systems. Okay. Then please read the textbook. It's chapter 1. So we in the previous class we learned about the content of chapter 1.1, 1.2, and 1.3. Okay. So new chapter. So in this class, we will learn about number systems of a digital system. So, what? So what is a digital system? So actually, it's simple, right? If a system handles digital signals, then this system is called a digital system, right? So which means that signals need to be represented as digital concept, right? So what is a digital signal? A signal value, like so actually a computer system is electric devices, right? So which means that we just manages the electric signals. So actually, inside of a processor, so we just handle voltage signals, right? So voltage signals, but you know the voltage signal is just a analog signal, but we just understand that the high voltage, like the VDD, is the one, and then low voltage, so ground as 0. So we can understand the ground, we can represent the ground voltage as 0. So we just use the two values, 1 and 0, in digital systems. So this is the digital world. So in the real world, we use some numbers to represent a certain data and then a certain signal, right? We frequently use numbers. So actually, so in this class, we have 83 students. So I used number 83 in the real world. But this is the analog world. The real world is the analog world. So we use some decimal number system. But in the digital world, so digital world just use two kinds of data, 1 and 0. So which means we need to use the different kinds of number system to represent the data or signals. So digital logic or digital systems use binary numbers, obviously. Why? The binary number, so each digit can include only two values, 0 and 1. Why? It's because it's a binary number. So in the decimal number, each digit can represent 0 to 9. So 10 different kinds of numbers. But in the binary number system, each digit can include only two kinds of numbers, 0 and 1. So it's similar to the digital signals or digital concept. That's why we use binary number systems in digital systems. obviously, actually obviously. So all data and all signals are represented as binary number systems in digital systems. So which means that the analog, so you know, but we are living in real world, so it's an analog world. So analog signals need to be converted. Okay, converted. So converted means that it changes or so it's transformed to the digital numbers or binary numbers. Okay, it's because in the analog world we just use the some very continuous numbers or very continuous signals. Let's suppose, for example, like the 1.123 4 blah blah blah. But these signals or these numbers need to be converted into the binary numbers or digital signals. Okay, so in this class, in the today's class, so we will learn about the binary number system. But I believe it's not difficult. So I believe so actually everyone learned about the binary number system, right? So this slide shows the conversion from analog signal to digital signal. So this is the analog signal. So as you can see, analog signal is a continuous signal. So by time, this is the time. This is time. By time, the signal values change continuously. So this is analog signal, the real signal. But in order to use, so we use electric devices, digital systems in the real world, right? So which means that this analog signal, in order to use our digital systems, and then in order to interface with some analog world, these analog signals need to be converted into the digital signals, right? So that means digital systems understand this analog signal like other manners. So we already know that this analog signal includes many different values, right? So this value is different from this value A, and this value A is different from the value B because it's a different value. But it is possible in the analog signals because, as I mentioned, the analog signals can include many different values and then continuous values. But when a digital system understands this analog signal, this analog signal needs to be converted. It's transformed into the digital signals like this. So in the digital signal, we have only 1 and 0 value. So the easiest way is to just set the threshold value. It's called the threshold, and then based on this threshold value, and then compares the value of analog signal with this threshold value. And then if this analog signal value is higher than the threshold level or threshold value, then we can say that, oh, this is the digital value 1. On the other hand, if this analog signal value is lower than the threshold value, then we can say that, oh, this value is the digital value 0. It is because commonly digital value 1 represents high value and then digital value 0 represents low value. So I mentioned that, oh, this signal, this value is higher than threshold, so it's 1. Oh, this value is lower than the threshold value, so it's 0. So we can we can convert the sorry analog signal to the digital signal like this. Okay. So and then if the analog signal is converted into the digital signal, then these digital signals are processed or handled in the digital system. So I mentioned processed or handled. So what does that mean? So it's like a function of black box. So we can understand the function like this. So like y equal f. F means the function. Okay, f x. So x is the input of a function, and then y is the output of a function. So it's like this. So this is the function, so or module of a digital system, and then input signal. Input signal is given to the a module of a digital system, right? So it's a function, but digital system receives digital signals. So this is the digital signal, and then what is the output of this module? The output of this module is also a digital value or digital signals. So inside of a digital system, all data and all signals are represented as digital signals. So which means that we need to use binary numbers. Okay, so binary number. So as you can see in the slides, analog information like some sound, light, voltage, and current. So these signals are converted into the digital signals. So, which means actually inside of a digital system handle binary numbers, not decimal numbers. Obviously, right? So what is the binary number? What is the binary number? So each digit, each digit can have only 0 and 1. That is the definition of a binary number. If a digit becomes 2, then we need to generate the carry. Okay? So I will explain later. So then let's start from the real world number system. So in the real world, we use decimal number system. Okay, so what does that mean? What is the decimal number system? So we write the 1, 2, 3, 4. So this is the 1234, right? So actually, this is the digit of digit. Okay, so this is Charlie in Korean, digit, and then actually in the binary number system, each digit can have a numbers. Each digit can include numbers from 0 to 9. This is the definition of a binary number system. Then, so this is the example, the 5,374. So what is a magnitude of this number? So we can represent the magnitude of this number like this, right? So obviously, so it's kind of very so like because elementary school mathematics, right? So then, but we can see the magnitude of each digit in this equation. So what does that mean? For example, this digit 5. The number for this digit is 5. Then what is the magnitude? Magnitude of this digit. The magnitude of this digit is the 5 multiplied by 10 to the power of 3. 5. So this is the 10 to the power of 3. Because the base of this decimal number system is 10. And then each digit represents the power of 10. Right. So it's 10 to the power of 3. Finally, number system is the same, right? So each digit can have 0 or 1. Okay, it cannot include 2 or 3 or 4, some other numbers. So it can have only 0 and 1. So this is the example 1101. So this is a binary number that includes 4 digits. Okay, and then as I like the previous example of a decimal number, this binary number can be represented like this. Okay, this is the magnitude of a binary number 1101. And then like a decimal number, each digit, the magnitude of each digit is equivalent to the power of 2. Because 2 is the base of a binary number system. Okay, so with this digit, the number is 1, and magnitude of this digit is the 1 because this number is 1, and then multiply by 2. So this is the base of a binary number system. And then to the power of 3. Okay, because it's a 1, 2, 1, 0, 1, 2, 3. Power of 3. Okay, so it's the same, right? So, and then because the digital system handles binary numbers, and we can just memorize. We can just memorize the powers of 2 because these numbers are frequently used in the computer world. Okay, computer systems. So, and then, but I believe you can easily memorize these power of 2s. Okay, like this. Actually, I recommend you to memorize until this one or this one. So if possible, then you can memorize until 2 to the power of 15. Okay. So why? So because we frequently use a decimal number system. So decimal number systems are very familiar with us. So we can easily calculate the magnitude of each digit of a decimal number. But but as a computer engineering student, we will frequently handle binary numbers or binary data. So that means many data will be represented as binary numbers. Then if we just memorize this power of 2s, then we can easily convert the magnitude or some data of the binary number to the real number. Okay, so I recommend you to memorize the powers of 2. Then so sometimes we need to convert the binary number to the decimal number. I think it's easy, right? So how can you convert the 10011 to the decimal number? I mentioned that each digit has the magnitude, right? So this is 2 to 0, 2 to 1, 2 to 2, blah blah blah. Then we can write the equation like this. I will not write. Oh, where is that? So it's because this is the fifth digit of the binary number. So this is the 1 multiplied by 2 to the power of 4, and then 1 multiplied by 2 to the power of 1 plus 1. That's because the 2 to the 0. So we can calculate the result of this equation. So we can easily calculate the convert the binary number to the decimal number, right? And then how? How can we convert the decimal number to the binary number? We can divide this number using base, okay, 2. Then, so 23 and remainder is 1, and then 2, so 1, 1, remainder 1, and then 2, and then 5, remainder 1, and then 2, 2, 1, 2, 1, 0. So this is the binary number, right? So this is the 1, 0, 1, 1, 1, 1, and base 2. How can we use this method? So I repeatedly divide the number using the base of binary number, right? Right. So it means the first two represent the remainder of 1. So because I just divide this 47 using the binary number 2, then remainder becomes this 1, right? And then after that, I also divide the quotient of this division using another 2. So which means that it is equivalent to, so I divide this number using 4, right? That is the 2 to the power of 2. So then remainder is 1. So by dividing the numbers using the base repeatedly, the base is 2, then it's similar to the magnitude of this digit. So, but I believe you are familiar with this method, okay? So actually we can easily convert the decimal number to the binary number, or this binary number to the decimal number, okay? So this method 1 and method 2. So method 1 is to find the largest power of 2 that fits and subtract repeat, but we can, in the previous example, I used the method 2, okay? So then let's think about the range of a number. So why is this? Why do we need to consider the range of a number? Why? So it is because a digital system. A digital system is hardware system. So what does that mean? We need to use the hardware resources to implement a digital system, and hardware resources are fixed. Do you understand? So actually when we learn the mathematics, then we can use the decimal number system, but we can use any ranges of decimal numbers, right? Like the 1, 2, 3, 4 multiplied by 10, and digit is increased like the 1, 2, 3, 4, 0 in the real world, in math, right? But actually, so you need to understand. So actually, we are learning about the hardware, and then enough to handle a certain digit of a number, then the hardware resources are used for handling a certain digit. And then these hardware resources are fixed. It's not a software. In the software that we can use so any numbers. Actually, it's not true in C, but in Python we can use any numbers. Okay, but in the hardware resources are fixed. So if a certain hardware resource is used for a certain digit, and then if a digit, but then we cannot increase, we cannot change this hardware resource. Okay, it's fixed. So for example, this is a hardware module. This has some function. It performs a certain function, and then it receives binary number or binary data. But this hardware can only handle 8 digits of binary number. Then we cannot give 9 digits of binary data to this hardware. It is because this hardware is fixed and then implemented for only handling 8 digits of binary numbers. So that's why we need to consider the range of a binary number or range of numbers in the hardware system, right? You understand? So, so let's think about the decimal number, n-digit decimal number. Then how many values? So n-digit. So for example, if we have a 4 digit of decimal number, then what is the maximum value that can be represented with this 4 digit decimal number? 9999, right? So this is the maximum number that can be represented with the 4 digit decimal number, right? So which means that the range of this decimal number is the 0 to 9999. So then how many numbers can be represented using this 4 digit decimal number? So it's 10 to the power of 4, right? So that means that we can represent 10 to the power of 4 decimal numbers using 4 digits of decimal number. So then how about the n digit? Is how many values? 10 to the power of n, right? And then range is the 0 to 10 to the power of n minus 1. This is the range that can be represented using n digit decimal number. Then how about the binary number? Actually, it's not important. So actually, we are learning about this system. Then we need to consider the range that can be represented using fixed binary number. So n bit binary number. So you can find the bit here. Bit is the actually binary digit. Okay. So how many values can be represented? Obviously, 2 to the power of n, right? Because the base is 2 and then it's the same, actually in the same way. So that how you can represent the 2 to the power of n different values using n digit binary number. And the range, what's the same? 0 to 2 to the power of n minus 1. Right? So which means, if we just design a digital module that can handle the n digit of a binary number, then we can this system can receive the binary number from 0 to 2 to the power of n minus 1. So this is the range that can be handled by this digital module. So just to remember that this is hardware, and then each digit is also assigned to the hardware module or hardware resources, and then usually we cannot change these hardware resources in the digital system. So which means that if a certain digit or a number of digits is fixed in the digital system, we cannot change it. So then we need to consider the range of data that can be handled by this digital system. Okay. Okay. Then X. Actually, it's hexadecimal. So now, let's learn about the hexadecimal number. So what is the hexadecimal number? The hexadecimal number means that the base is the 16. So until now, so we learned about the decimal number system, which means that the base is 10, and then binary number system, the base is 2, and then now we will learn about the hexadecimal number system, and then it means that this is the base is 16. Then why do we need to learn about the hexadecimal numbers now? So I mentioned that we need to learn about the digital systems and these binary numbers. It is because digital systems can only have two different values, 0 and 1, and so obviously then that's why we use binary numbers in the digital systems. And why hexadecimal? Hexadecimal numbers are also frequently used in the digital system. So that means hexadecimal numbers are frequently used in the computer systems, computer programming. And why? So what is the problem of a binary number system? Each digit can represent only 0 and 1, so which means that in order to represent a large number, we require a large number of digits, right? So for example, I want to represent a very large number like the billion using the binary number. How many digits are required? Many digits, okay? So the problem is that in the binary number system, in order to represent a large number, then this large number requires a large number of digits, like 1 0 0 1 1 1 1 1 0 0 0 1 1 0 0 1 1 1 1, something like this. So in order to reduce the number of digits, we frequently use hexadecimal number. So why? The hexadecimal number, the base is 16, and then 16 is the 2 to the power of 4. So which means that, and then each digit of a hexadecimal number can have 0 to f, okay? Because 16 different numbers, okay? So because the base is 16, using a single digit of a hexadecimal number can include the 4 digits of binary number, right? because so 0 is 0, 0, 0, 0, 0, 1 is 0, 0, 0, 1, and then F is it's 1, 1, 1, 1. So which means using one digit of hexadecimal number, then this one digit of hexadecimal number can represent 4 digits of binary number. So which means that we can reduce the number of digits if we use the hexadecimal number. So that's why in the computer system we frequently use hexadecimal numbers. Okay. Because of this reason. So this is the some conversion table. So this is the hexadecimal number digit, and then it is equivalent to the 0000. So as you can see, you can find that the one digit can represent the 0002 1111. So which means that we can compress, we can reduce the number of digits if we use the hexadecimal number system. So in this course, you are learning about the system. So it means that you can easily observe binary numbers. Also, you can easily observe hexadecimal numbers. I frequently use hexadecimal numbers. Is it because if we just use the binary numbers, then the length is too long. Okay. So this is some conversion rule, and then also you can apply the same method. Okay. Oh, so this is some different. So this conversion is the hexadecimal to binary conversion. So and then this is the example. This is the hexadecimal number 4AF. Okay. Then how can you convert this one to the binary number? So it's easy. So if we use the previous table, so we can easily observe that F is mapped to the 1111, right? So we don't need to calculate the for this conversion, right? Because F is the 1111. Okay, so I mentioned that one digit of hexadecimal number is equivalent to the 4 digits of binary number. And how about the A? So you can memorize actually. A is the 1010. Okay. So in the previous table, A is the 1010. Okay. And then 4 is the 0100. So and then by merging this conversion like 1011 0 0100 1010 1111 and then 2 is 2. So this becomes the binary number. So we can easily convert the hexadecimal to the binary number. Okay. And then also with the same way, it's the 4 multiplied by 16 power of 2 plus A. A is the 10 multiplied by 16 power of 1 plus F. F is the 15 and then multiplied by 16 power of 0. So the decimal number. Okay, so this is the hexadecimal number. And then, so if you study hard for this course, then I believe you can easily memorize this table. Also, I believe you can easily memorize the powers of 2 because we frequently use these numbers. Okay. Okay, so then let's learn about some terminology of a digital system. Okay, so so in the digital number system or in the digital data, I will frequently use some terminologies such as the bits, bytes, and nibbles. But I believe you are familiar with these two terminologies like bits and bytes. We frequently use bits and bytes to represent the size or uh, number of digits of binary data or binary numbers. And then sometimes we can use nibbles. So just to memorize, just to memorize this definition of the terminology. So what is bit? Bit is the one digit of a binary number. So actually it represents the binary digit. That's why it is called the bit. Okay, so this is the bit. So bit means the one digit of binary data. So this is the example. 10010110. So this number has 8 bits, okay? Because there are 8 digits, and then this is the binary number. So we can say that, oh, this data includes 8 bits, okay? It's a bit. Bit is the some bit represent the one digit of a binary number, and then we frequently use bit for representing the magnitude of data, size of data. Okay, and then so there are many bits in this number, right? So there are 8 bits, and then this bit is called the least significant bit, and then in the abbreviation form it is called the LSB. Okay, so if I mention LSB of a number, then it represents this last bit of the binary number. It is called LSB, the least significant bit. Okay, and then I frequently use the MSB. So this is the most significant bit. It's called the MSB. Okay. So if I just mention MSB of this data, then it represents the first bit of a binary number. Okay. I will frequently use the MSB or LSB. Okay. It is because this part is sometimes is the important part for representing data. Okay. And then we call 8 bits of binary data as byte. Okay, byte represents the 8 bits, just 8 bits. So it means the 1 byte equal 8 bits of binary data. Okay, and then nibble represents the 4 bits. So this is so 1 binary digit is the 1 bit, okay? It's equivalent to 1 bit, and then 1 hex digit. How about the 1 hexadecimal digit? 1 hexadecimal digit is equivalent to 4 bits, as we learned, right? So 4 bit, and then it is also equivalent to 1 nibble, right? And then how about the 2 hexadecimal? Who hexadecimal digit? 2 hexadecimal digit makes 1 byte equal 8 bit. Okay. So in the digital system, well, we frequently use bit or byte. Okay. So this is some very base unit for representing the size of of binary data or size of binary number. Okay, bit is 1 bit and byte is 8 bit. Also, in the binary number system, we frequently use the very large number, and then so we can just represent the very large number like the kilo, mega, giga, or tera. So it's very familiar, right? So sometimes we frequently use the my smartphone has 6 gigabytes of memory, right? 6 gigabyte. So what does that mean? So B, the large B, is a capital B represents the byte. Okay. So which means it's 8 bit. And how about the G? G represent giga. So what is a giga? So as you can see, giga represent the giga is equivalent to 2 to the power of 30. Okay. And then it's a 6. So what does it mean? 6 gigabyte. It represents the 6 multiplied by 2 to the power of 30 byte. So this is byte, so it's the multiplied by 8 bit. So what does that mean? Oh, my smartphone has 6 gigabyte of memory. So we can store binary data, we can store digital data in the memory, and then this is the size of the memory, 6 gigabyte. The capital B represents the byte, and then lowercase b represents the bit. Okay, so it means the size of my memory, so smartphone's memory is the 6 multiplied by 2 to the power of 30 multiplied by 8. So which means this memory can store this amount of binary digit. Okay. So we frequently use giga, kilo, mega for representing very large binary number. Now what is kilo? It's 2 to the power of 10. Why? What is kilo in decimal number? Kilo is 1,000, right? So 10 to the power of 3. But in the binary number system, kilo is 2 to the power of 10. Why? So sometimes, so so in the SSD, so SSD size is represented as the some gigabyte or terabyte, but the actual size is different sometimes. So why? Why kilo is 10? Why is kilo is 2 to the power of 10, not 1,000? Actually, in the real world, kilo represents the 1,000, right? So it is because 2 to the power of 10 is 1,024, and then this magnitude is similar to the 1,000, right? So 1,000 is kilo. So that's why in the binary number, 2 to the power of 10 becomes kilo. Okay, it's K. Then mega is the 2 to the power of 20, because the mega is the in the decimal number system, mega is 10 to the power of 6 is the 10 to the power of 10 multiplied by 10 to the power of 10. Kilo multiplied by kilo is mega. So 1 mega is 2 to the power of 20. Okay. So just to remember that in the binary number system, K represents the 2 to the power of 10, M is mega, is the 2 to the power of 20, G is giga, 3 tera, peta, exa. Okay. These characters are used for representing very large number. Okay. So you need to be familiar with the kilobyte, megabyte, and gigabyte, and terabyte. It is because the size of data is, so this size of number, the binary numbers are very frequently used in the computer system, right? So 1 kilobyte is equivalent to the 1024 byte, okay? Mega and giga. So, and then, we frequently use this unit for representing the size of memory or size of storage in the computer system. Okay, 1 tera to the power 40, peta, exa, and zeta. So it's very large. Okay. Then estimating power of 2, powers of 2. So what is the value of 2 to the power of 24? So using the so in order to represent this large number, so actually is the 2 to the power of 20 multiplied by 2 to the power of 4 is a very basic math. So this is giga, right? Right? No, this is mega, right? Mega or giga? It's mega, right? It's kilo, mega, giga, tera. And then kilo is 2 to the power of 10. Giga is mega is the 2 to the power of 20. And giga, 2 to the power of 30. Kilo, mega, giga, tera. Okay. So this is mega and this is 16. So it's 16 mega. Then, how large of a value can a 32-bit integer variable represent? So what's the maximum value? It's a 32-bit integer. So if you are familiar with C, then the C has some data type called integer. So actually in Python we can handle numbers in Python, but Python does not have any data type actually. So we can just handle numbers or characters, but in the Python, the range of numbers is not restricted. Usually, it can be restricted, but it's very large. But in C or C++, so this C++ is some advanced version of C. In the C just to define data type, and then by this data type, some bits are assigned to this data. Okay, so for example, this int a, it means that the variable a is declared as integer type number, but we just assign 32-bit to the integer data type. Then what is the maximum number that can be represented as integer data type? It's 2 to the power of 32 minus 1. It's because we can represent the 0 to 2 to the power of 32 minus 1. That is the range of number that can be represented using 32-bit data. So C, so the C is tightly related, tightly coupled with the hardware, but Python is a little bit different. That's why the Python is so easier to run. Okay, and then the last example is assuming you have 4 GB of main memory in your computer, then how many bits are required to represent the address of main memory? So do you understand this question? So what is the address? So just to remember that in the normal computer system, 1 byte of data is equivalent to the one of address. So what does that mean? So actually you can understand the memory is some storage. Memory is a storage space that can store digital bits. Okay? And then we just make the storage space, and then that means that we can just assign memory. Okay? Then with the 4 GB of memory, so which means that this main memory can store 4 GB of binary data. Okay? And then actually in order to figure out the location of data, then we use address. Okay? And then address number 1 is assigned to the 1 byte of data. So if, for example, address 0 is mapped to the first 1 byte of data. 1 byte of data. Okay? So which means that it's the first 8 bits of data is assigned to the address number 0. And then the next 1 byte of data is assigned to the address number 1. So that's how the address is represented in the computer system. Okay? So you can just remember that in the address of the memory, then the address 1 is mapped to the 1 byte of data in the computer system. Okay. This question asks that your computer can store 4 GB of data. Then how many bits are required for address for this computer? So which means that this is 4 GB of memory. So which means this memory can store 4 multiplied by 2 to the power of 30 byte. Okay, so which means the address needs to represent until this number, right? So this is the maximum number that can be represented using address. Do you understand? Then how many bits are required? How many bits are required for representing this number? Actually, the address starts from the 0. Okay, but in the computer system, numbers start from 0, not 1. Okay. So, in order to represent this large number, we require. So this is 2 to the 2. So we require 2. Actually, this is equivalent to the 2 to the 32. So which means that we require 32 bits. Because with the 32 bits, we can represent the 0 to 2 to the power of 32 minus 1. Okay? So do you understand? So this memory can store 8 GB of data, and then 1 byte of data is mapped to the address 1, and then in order to represent the address, so which means that address needs to represent the 0 to 2 to the 32 minus 1. So which means that this value, this range of number can be represented using 32-bit binary number. Which means, for the address bit, for the address data, we require 32 bits. Okay. Okay, so I hope you can be familiar with some the binary representation. Okay, so this is actually the basic representation or basic some practice, the basic practice in computer engineering area, computer science area. Okay, then sometimes I believe you are not familiar with this question because you did not learn about the computer architecture yet, but sometimes uh, we can say like this. So we can use the binary representation for describing computer systems. Okay. Okay. So I will stop here. Any questions? Okay. Good. Okay. Thank you for your listening, and then see you in the next class. 감사합니다.